Good morning, folks. This is Todd Coburn of Cal Poly Pomona with Lecture 12 of Aero 3271. Today we're going to be continuing our study into fasteners, and we're going to focus on tension-loaded joints and preloaded joints. And so let's see what we have here. So let's start off by imagining that we have two plates clamped together with a single bolt. Okay, we've got the bolt. If the bolt, we can tighten the bolt until it just touches the plate, till it's just barely touching. And then if we continue to turn the bolt, the nut will continue to advance, which will squeeze the plate. We'll find that as we squeeze the plate, that's going to cause a compressive force on the plate, and the plate is going to push back against the bolt. Like imagine somebody grabbing your arms and pushing them against your body, and you're pushing back. You're going to push back with the exact same force as they're pushing if you hope not to move. If you push with less, you're going to be getting squeezed, and if you push with more, you're going to be expanding. In the same way, those plates are going to resist that. Since plates are people too, they're going to resist that squeezing action, and they're going to push back with exactly the same force. So one of the first ideas we need to recognize is when we're preloading a joint, which means we're tightening with no external loads, the force of the preload is the amount of clamping force in the plates, or whatever members are being attached together, and the bolt will see the exact same tension force. That tension force is going to cause a pulling stress, a tension stress in the fastener. It's also going to cause bending of the fastener head. As that bolt is being pulled through, it's going to bend down like this, and same thing with the nut, a little bit of bending, which is actually going to work the threads. Okay, so as our bolt tightens, it squeezes the members. They push back with the same force. So the force in the bolt is the same as the force in the members, and we can just identify it as the initial or preload PSI. Got that? So we already know that when we have a preloaded joint, the bolt force and the member forces are the same for preload. Okay? And yet, unless the stiffnesses are the same, which is almost never going to be the case, they're going to deform different amounts. We know that the deformation under axial load is PL over AE, and therefore the actual deformation for that load is going to be a function of the length that's effective, that's being squeezed, the area that's being squeezed, and the modulus. Okay? Now, this is going to be fairly straightforward for the bolt calculations. It's going to be a little bit more work for the member calculation, but we're going to keep it simple and come up with an approach that is used in industry and that will take you there every time. So our deflection is PL over AE. The spring constant is just force over deflection. So we can write, combine those equations to find that the spring constant is AE over L. We're also going to use this idea in finite elements when we get there if you come back for more punishment. So we actually can write that the stiffness of the bolt is just the area of the bolt times the modulus of the bolt over the length of it, and the stiffness of the members that are being clamped is just the area of the members, the E of the members, and the length of the members. Now, this looks pretty benign, but actually there are usually multiple parts that need to be assessed to get the right spring constant. So usually our equation is not going to be quite this simple. We're going to need to put some things together using these equations, but putting all the pieces together. So let's start with our bolt stiffness basics. Our first goal today is to learn how to determine, to estimate the stiffness of the bolt. Our second goal will be to learn how to estimate the stiffness of the members, and then we will learn how to put those together and also to evaluate preload. So you can imagine if we have an axial member that the area is simply the cross-sectional area. Pi d squared over 4 if the shank diameter is d. However, if you look at a bolt, only part of it has that shank diameter. The other part is threaded. So what we're going to need to do is determine what part of this gets the shank diameter and what part of it gets the thread diameter, okay? So if we take a look at this, we can say the total length. So the first thing we need to understand is the total length that's effective. It's not the total end-to-end length of the bolt. It's the length that's effective for squeezing the parts, or actually the length of the bolt that is actually getting stretched. Now, this actually is rather complicated because there are going to be some flux in the head. There's going to be some flux in the threads underneath the nut. We're going to keep it simple. So what we're going to do is identify the mating surface or the clamping surface of the head and the clamping surface of the nut. If you look at this little figure here, you see these are shown. Right here, we have the clamping surface of the bolt head and the clamping surface of the nut head. You see that? So you'll notice when this bolt is tightened, it's going to stretch the bolt from this line of action all the way to this line of action. Now there will actually be some squeezing of the bolt or some stretching of the bolt in underneath the nut, and there's also going to be some flex in the head as it tries to deform. But we're going to consider those negligible, and we're just going to use this length of the bolt as the distance between the two clamping surfaces. If there was no washer, then it would be, let's say we draw another one with no washer, then our distance is just this, okay? So for bolts, we're going to go from clamping surface of the head to clamping surface of the nut. And when we get to members shortly, we're going to actually come up with a stiffness term for each and every element. Like for this washer, this plate, and this washer. Everything that's in that between these two squeezing lines or planes, we're going to get a K for each of those. We're also going to get a K, but right now we're on the bolt piece. So what we're going to do is get a K for each different part of the bolt. So between these two surfaces, we have this much bolt, which has a shank diameter, and we have this much bolt, which has a thread diameter. That's our thread diameter. This is our bolt diameter. So we actually have two elements. We're going to need a K for the bolt or the shank, and we're going to need a K for the thread. The K for the shank is going to use the area of the shank, and the K for the thread is going to use the area for the thread. Both of these are going to have the same exact E, and we'll find that the length of each is different. But the summation of these lengths is going to be equal to the total effective bolt length. Do you see that? Now you need to be a little careful in my nomenclature here. I'm often using a subscript B for the bolt. I also often use a subscript B for the shank. And that might be better to use a K sub S for the shank. But you'll notice throughout my lecture I'm not doing that. I probably should upgrade that in the future to make that a little clearer. But as long as you understand that, that's the important thing at this point. Okay? So what we see here, this A sub T is the area of the thread, and as I said, A sub D is what we're going to use for the bolt shank area. The length of the thread is not the total length of the thread, it is the length of the thread that's effective. So you got to be a little careful with this. So if we get a bolt, we're going to get, the bolt, remember, is called out with a length. And the length of the bolt that it's called out is actually this length. That's the length of a bolt when you see a bolt call out. You're also going to have a thread, and usually what you're going to get is a thread length call out. You could also get a shank call out, but often it'll talk about how much thread there is. Now, we're not actually going to use that value, at least we are going to use it, but what we're going to need to do, now if this shank went through the parts, let's say we have two members, and the bolt comes in here, and the shank goes down to here, and the threads are down here, and our parts are way up here, then there's no clamping action. So what we're going to find is the shank always needs to end. You need multiple threads in the clamping surface. So you'd rather not have threads in here because those are going to wear this part and make it not work as well. But if you don't have threads in here, when this squeeze is on, it's going to run out of threads and you won't get enough clamping action. Okay, so what we're going to do is we're going to go and say, all right, we got a bolt and we know how long the bolt is, and we probably know what the thread length is. Then what we're going to do is figure out, okay, what's the distance, L sub B, from between the two clamping surfaces. And we're going to say, all right, the distance between the two clamping surfaces, that means the length that we're going to use for the shank when we calculate our K, right? K is equal to area of the shank, E of the shank, over L of the shank. And the length that we're going to use for the shank stiffness is going to be all of that shank length, right? Which is the length of the bolt off the shelf minus the length of the thread off the shelf. That's how much shank we have. That goes in here. Then what we're going to do is say, okay, what is the effective length of the joint? I'm calling it L sub B up here, and that's going to be the distance from the two between the clamping surfaces. That's going to be, we're going to get that value, right? We can measure that from our thing, from our sketch. And then we're going to need, what's the length of the thread? The length of the thread is going to be the total, it's going to be the length of the effective length, right, which I'm calling LB up here, minus the length of the shank. That's how much threads are engaged. So we need that length for the part that's threaded and the other length for the part that's the shank. So this is the length of the shank, and this is the length of the thread that's effective. And we called all of this length, in this picture over here it's L sub B, but actually a better term is L effective for that joint. Okay? You got all those ideas? It's very important. I think this discussion right here might be the clearest I've pitched it, so it may be clearer than your manual. So make sure you understand that. Watch that again if you need to. All right. So we've got the area of the shank, and we're going to have an area of a thread. And we're going to use those. So actually right here, I'm going to give you better nomenclature right here. Let's call this the shank diameter. This is the nominal diameter of the bolt. So this is going to be the shank, shank. This is of the shank. This is of the shank. Of course, the whole bolt has, all the bolt has the same modulus. So we could just use E bolt. This is going to be the area of the thread. This is going to be the length of the thread. Remember, the length of the thread is only this distance. You've got to determine what this distance is. Not that distance. Not that one. This one. That's our length of the thread that we need. Okay? And this we're going to call the length of our shank. And this, we could say this, but actually L effective is better. Okay? So this gives us our relation for the shank stiffness. This gives us our relation for the thread thickness. This is just the area of the thread. So if we have a non-aerospace fastener, we read it right off our table. Okay? You can actually find, yeah. Okay. Now, since we have two terms, we put our two stiffnesses together in the normal way that we learned probably back in physics in high school, which can be written this way. Anytime we only have two spring constants in our member, we can put them together with this. If we have more than two, then we will need to use, put them together like we do springs as well, and we'll show that in a moment, because often we're going to have two elements for the bolt, the shank and the thread, and we will have at least two elements for the members. We'll usually have two parts that we're clamping. They might be plates, they might be just a flange on something, and then often there will be washers, there may be splice plates and other things, okay? We're going to need to, for the members, we're going to need to do a little more work. But this is the key for bolts. I'm going to erase this, and then I'm going to permanently augment this with, well, let me turn this back on, and hopefully this reminds me to upgrade this both in your thing and in your handbook. For the shank, we're going to call this shank. We're going to call this shank. We're going to call this shank, shank, bolt, shank. And over here, that means this is shank, 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 bolt. This is bolt, and this is thread, thread. Shank, shank. Okay? This is the shank, and this is the shank. Oh, D, we said D, LD, not B is what we're using, yeah. Regardless, shank might be a better. Fine. Okay, got that? All right. Okay, so for simple joints, this one, we see the effective length is going from end to end again, and from clamping surface to clamping surface. The clamping surfaces are set apart by a washer in the second picture, and now what we're looking at is the members. Now, members are going to typically have more than one member, and we're going to put them together like springs again, and we're going to get this relation. This is the relation that we need for members. We're going to have multiple terms. What we're going to need is the K of every member in the mix, and we're going to put them together with this relation. So when we're all done, we're going to get K of the members is going to be 1 over the sum of the 1 over K's. Okay, so the question is, what K do we use? What we're going to do is we're going to fan out our load. We're going to start from the outermost edge of the head, and we're going to fan out at some angle. Okay, now if we just assume that only what's under the head, let me do that first. If we assumed that only what's under the head is effective, then what we would do is we'd say, okay, underneath the head is our effective column of material. Now the head usually looks something like this. It's often not round, but we're basically going to go and assume, pretend that right here, this diameter of the flats, whatever this dimension is, we're going to pretend that's a round sample. That's the diameter of the head, and we're just going to take everything underneath it, and we would find the stiffness of that. If we use this approach, we would get a hollow cylinder where that inside hole is the hole size, and the outer hole is basically the diameter of the head between the flats, right? And then we could take this, and actually we know we have at least 2 materials being clamped together, which means we've got 2 elements. We would come up with the area of that and then calculate the relative stiffness. Now we're not going to use that approach because it's too conservative. If you go and you jump on your mother's bed or stand on your mother's bed for a minute, you're going to find out her bed is nice and neat. She probably made it this morning. And then you jump up here with your nephews, and what happens is it doesn't just compress here, it compresses here as you move downward. It compresses like this. So not only does it compresses the most right underneath your feet, but it compresses nearby as well, less and less as you move away. You could imagine that the loading underneath you, the effective diameter underneath your foot, is fanning out at some distance. Now, usually the bed is on some surface like this, so it keeps fanning out. But imagine for a minute that you jump on a bed and somebody is pushing on the other side, such that as you do that, you fan out that load like this. That's what we're going to do with the bolt. Instead of doing this, what we're going to do is fan that load out. So I'm going to clean this up, and I'm going to show you what that looks like. All right, so if we have a bolt like this one, what we're going to do is start with the outermost surface. Remember, from clamping surface to clamping surface, that's our L effective, our total effective length. We can see we're going to have that much thread and that much shank for this bolt. But what we're looking at now is not the bolt. We've already done that on the last slide. Now we're going to look at the members. So for the members, between that same clamping action, what we're going to do is from this clamping action at the head, we're going to fan this out at some angle. Now, some angle alpha. And we're going to fan this one out at some angle alpha. And we're going to fan this one out at some angle alpha. And this one out at some angle alpha. Okay? What's going to happen is, what that means is, our load, we could imagine that it really clamps up as if it's only like this. Now, values of alpha are very commonly taken to be 30 is commonly used, and a lot of people like that number. They feel it's conservative. 45 degrees is commonly used as well, and 60 degrees is commonly used. Less so for 60 degrees. That means you're fanning out even more. Okay? Now, this is thought of as conservative, so a lot of folks might push you to use that kind of number. This value is fairly representative, and the beauty is when we have something that's 45 degrees, tangent of 45 degrees, right? It's a nice simple relation where for a 45 degree angle, these two dimensions are the same. That's going to make our analysis easier, and all this is grossly approximate anyways. So why make it complicated if you're not getting a benefit? So what we're going to use is we're going to assume in this class that alpha equals 45 degrees. You should be able to use other alphas as well. If you get an industry, they may want you to use 30 degrees or some other number, but 45 degrees is what we're going to use in this class, and it's good enough for government work. So I'm going to clean up the slide again, and redrawing what we're talking about, we're basically going to say, okay, this joint from clamping surface to clamping surface, we're going to find the outermost point of the head. We're going to fan out at our angle alpha, all of these, okay? Just like that, okay? And then what we're going to do is we're going to go ahead and use that same. Now we could say, hey, what's the area, what's the stiffness of this cone? Actually, I'm going to show you the Ito method, which is a conic method, the stiffness of a cone, a hollow cone like this. The problem is you'd get a hollow cone above and a hollow cone below, and it's a complicated equation, and it doesn't add that much to a relatively approximate thing. What we're going to do is we're going to figure out an effective diameter, and we're going to pretend that each element in here is just a cylinder in compression. Now, if we use this diameter here, we already said that would be too conservative. If we use this outer diameter down here, that would be too under-conservative. What we're going to look for is what's this dimension, what's the diameter at the middle of each and every one of these clamped members. And we're going to use that as our diameter for each conic cylinder. So if we're using at 45 degrees, let's just focus here. Here's our head, and we're fanning out at 45 degrees. Since it's 45 degrees, that means this dimension is the same as that dimension. What that means is we're looking for what the dimension is when this value here is t over 2, the thickness of that member over 2. That means this is t over 2. What that means is the radius grows by t over 2. That means the diameter grows by t over 2 plus t over 2. Generally, according to new math, is just t. So we can say, oh, this is really simple. If we use a 45 degree alpha for our spreading load, then the effective diameter for the upper plate is going to be the d of the head plus the thickness of the part. And the d of the other plate, effective of the second plate, is going to be d of the nut plus t of the plate. And that's the lower plate, right? This is the upper plate, this is the lower plate. And if we did that from the washers, there's two ways we can do washers. One of them, let me draw another one. One of them, let's say we have a really, really thin, wide washer on top of our plate. Well, in that case, if that washer is really thin, it's not going to be stiff enough to give us a lot of clamping, and we would just go through and use our same 45 degree angle through the washer. What that means is we would calculate a new diameter at the middle of the washer for that little one, and a new diameter at the middle of each clamp member like we did before. If our washer is thicker, like let's say here's our head, and we have a shallow, thick washer like this, then probably this washer is stiff enough that it can transfer all the load. In that case, we'd use the full diameter of the washer as its stiffness, and then we would fan out the load from below it. This is actually the way we're going to do it in this class. We're not going to do it this way unless I tell you to do it this way. So what we're going to do, whenever we see a washer, we're going to say, okay, what is the outer diameter of the washer? What is the inner diameter of the washer? Let's calculate the stiffness of that washer by itself and this washer by itself. Then from the edge of the washer, we will fan out our load at 45 degrees. We will find the middle, so that means D now of the washer plus T is going to be the effective diameter of the upper plate. And we're going to say, okay, down here we already counted for the washer. We're going to fan out the load from the bottom of the washer, and that means diameter of the washer below plus the thickness of the lower plate will give us, this is of the upper plate, the D effective of the lower plate. And then we can plug those values into this equation. We'll get a K for the upper plate and a K for the lower plate. This will be the area, the effective area of the upper plate. This will be the effective length or the thickness of the upper plate. This will be the modulus of the upper plate. And then we'll get the same thing for the lower plate. We're using AL, EL over TL, right? And if there were other members, we would do that. We would have a term accounting for them also. Let's take this one step further. Let's say we have a set of parts. Let's say we have a plate and another plate and another plate. All of these are between washers and nut and bolt. Okay, and let's say we have threads going like this and shank like this. We'd start off with a bolt. K bolt will account for the length of the shank and its area and the length of the thread and its area. Okay, put those together, that gives us the K of the bolt. Then we're going to look at the members. In this class, remember, we're going to assume that each washer is fully effective. That means we're going to take DO and DI and we're going to calculate the stiffness of that washer. Probably the washer down here is going to have the same stiffness. Then what we're going to do is span out our load 45 degrees. It's 45 degrees. We need the effective diameter through here. So if this is member 1, 2, 3, the diameter effective for plate number 1 is going to be D washer plus thickness of the upper plate. Okay? So then we can get the K for the upper plate by using the area based on this diameter, the thickness of that plate, and the E of that plate. Now, D3 is just as simple. That's going to be the D of the lower washer plus the thickness of the lower plate. We use that to get the K of the lower plate, along with the area based on that, and the thickness of that plate, and the modulus of that plate. Now, D2 is a little trickier, because D2 starts at a different value. Remember, we're going to be fanning this load out. So what we're going to have to do, and sometimes based on the thickness of the part, one of these circles will be bigger that's fanning out. So we need to determine which of these two cone angles gives us the smaller diameter at the center. So we'll need to check. So we're going to need to come up with this. What's the diameter right here at the bottom of this plate? Well, the diameter at the bottom of this plate, D bottom, that we're not going to use, is going to be the D washer plus, remember, if we added the thickness of the plate, that would give us the diameter here, but to get the diameter down here, we're going to plus 2 thickness of the upper plate. That's the diameter of the bottom. If we want the diameter of the middlemost plate, D2, that's going to be DB plus T2. Now we also need to check down here, because D top of this lower plate is going to be equal to D of the washer plus 2T of the lower plate, And so D2, it might be this and it might be this. D top of the lower plate plus T of the 2, right? So we're going to look at these two values, take whichever one is smaller, and then we'll calculate an area based on that, and that will allow us, plug in all that in, to calculate K of the second plate. Then we'll use this to put this all together. We'll have 4 terms down here. We've got one for this washer. Oh, excuse me, 5 terms. One for this washer, one for this plate, one for this plate, one for this plate. So that's 5 terms, 3 member terms and 2 washer terms. We now, having all those stiffnesses, would be ready to analyze our joint. Make sense? So we already talked about this. We talked about this. We talked about all this. This is just another slide saying the same thing. This is saying this is the actual relation to get the effective diameter at the middle of the plate. It's D plus 2 times T over 2 tangent alpha. Now if alpha is 45 degrees, that simplifies to our easier equation D plus T. All right. We talked about this. This is that cone method. This method down here is out of Shigley on the bottom. And basically everything down here, we already set everything above this line, right? Everything down here is saying, what if we treat this as a cone that looks like this? That's more accurate, right? And then we got a cone down below. Sure, it's more accurate, but look at this. I've seen your work, and most of you, when you start sticking natural logs in things, you start coming up with bogus numbers. This has potential to better mass test results. However, it's complicated, it's easy to mess up. It obscures how clear this is of just coming up with an effective diameter and stiffness. So we're not going to use this. You're certainly welcome to use it in industry. We're not going to use it in this class. Okay? All right. So if we take a look at how this thing works, this is a little MATLAB program I wrote a few years ago. This shows for a given joint, and here I'm using, I think, a 30-degree angle, and look at comparing different methods. These are the different stiffnesses, and I'm comparing the cone method to like the method that I presented, but using a 30-degree angle. It actually is fairly close in the results. Okay? All right, next idea. So let's say that we have no preload on the bolt. What that means is we tighten the bolt up until it just touches the plate. New idea. So let's say that we tighten this bolt, we place the bolt through the parts, and then we thread it on until this nut just barely kisses this plate. We have no preload because we haven't squeezed the parts at all. It's just touching. If that happens and then an external load pulls these two plates apart, then all of the load will go into the bolts. These plates are not in compression, and any pulling, any separation force will go in the bolt. That means all of the external load goes into the bolt, and the bolt stress is just P over A. A is the area of the thread. Obviously, we have a tension stress all through the shank as well, but we're going to have a smaller area of the thread. That's smaller than the area of the shank. Therefore, that's usually where we will do our calculation for the critical stress. And we can compare the numbers using our normal margin of safety approach. Okay. Now, if we do have a preloaded joint, here's what's going to happen. Let's say we have a joint that's already under compression. If we preload the bolt, which means when we put the thing on, before any external loads come on, we squeeze that nut on. Remember, the bolt is in tension and the members are in compression, and the force of the values are the same. That plates are squeezed together and the bolt is stretched as that happens. Now, after this point, if we go and we pull on it with an external force to pull these two parts apart, then we're going to have a force, and that force is going to cause a deflection. Now, if you look between the clamping surfaces, you'll notice that between our clamping faces, right? So if we take this clamping face of the bolt and this clamping face of the nut, that's our L effective, right? All of that, anything in between is being squeezed. Now, if somebody pulls on these two members trying to pull them apart, then this is going to deflect. And what's going to happen is as it deflects, we're going to find a little deflection. You'll notice that deflection, that bolt is going to stretch by that extra deflection, and these members are going to release or expand by that same deflection. So the deflection in the bolt and the deflection in the members are the same. Now we know that because spring constant equal to P over delta, right? That means that the deflection is just P over the spring constant. This is one of the reasons we're going to need that spring constant. So we can write that this relation where the force in the bolt relative to its spring constant is equal to the force in the members divided by its spring constant. The total force that's applied is going to be P, that external load, and part of it will be in the bolt and part will be in the members, because the bolt will use some of that to stretch and the plates will absorb some of that to expand. So the member force is just the external force minus the bolt force. If we insert the number we had before, we can write it this way, which we can rearrange this way, which we can write this way, and this way, which can be written this way, which gives us our relations. These are our key relations these are the key relations for the bolt force and the member force. Let's take a look. First, we note what we have here is we have the preload, right? The preload, whatever preload was applied, was actually stretching the bolt. It was tension. And whatever preload was applied was actually compressing the plates. So it's positive for the bolt and it's negative for the plates. Then what we see is we've got the external load here in both of these equations. And what we see, this is the total stiffness of the joint, and this is the bolt stiffness of the joint. So this is the relative stiffness of the bolt to the total joint stiffness. So the force in the bolt was the external load times the bolt relative stiffness plus the preload, and the member stiffness is the external force times the member fraction of how much its relative stiffness term minus its original preload, which was in compression. This is causing tension on the joint, and this is causing compression on the joint. These are our two relations that we're going to use a lot. Now on the next slide, we're going to go look at these two terms, and we're going to give that a special name. We're going to call that C, okay? All right. So these are the two relations, and we now introduce the stiffness constant. You'll notice the stiffness constant is the bolt stiffness divided by the total stiffness. The joint stiffness constant is the bolt stiffness divided by the total stiffness. Okay. What that means is we can write these two relations in an alternate form. In a little shorter form, we can take that C, and that means the bolt force is just C times the external force plus the preload, and the member force is just 1 minus C, it's the rest of the fraction, times the external force minus the preload. Okay? Now these equations are all valid as long as our plates are still in compression. If they have any compression, if the member force is negative, that means it's in compression, and that means the spring constant is valid. Okay? If we ever get a zero force in the members, what happens is we have removed all of the preload out of the members, and if that happens, then actually all that external load immediately goes into the bolt itself. So as long as we have, so what happens is, let's say we have a bolt that's clamping together some members, and if we start pulling on the joint, it releases. As long as we have some clamping in the members, then the spring constant, C, joint stiffness constant, is valid. Now at some point we get to the point where there's zero preload in the zero compression in the plates. At that point, any more load just pulls the fastener away, which means all of the fastener is acting by itself. Let me draw something here. At the point where we have no load, right after that, if we keep pulling on the whatever is pulling, let me do it, draw it differently. Here's our bolt head, and we're actually pulling on this plate here with this force. And once, and let's say we had another part down here, and this is where our nut is, and the bolt's like this. So you'll notice if we have any gap, then that means you can draw a line through here, and that means the bolt takes all of this external force. It also still has whatever preload it has, which means the total force in the bolt is going to be the summation of those. Now this happens when we have a gap, but it also happens when we're in contact, zero gap, but all compression has been removed from these two members. So remember, this term is only valid if this term is negative. If this term is 0 or positive, then C is 0, and that means the members take nothing at that point, and this takes everything. Okay? Excuse me. C is not 0, C is 1. If C is 1, right, what that means is C is ineffective. That means this suddenly means the bolt takes everything. Because now the member stiffness doesn't matter. That means as soon as the preload, the compression is removed out of the members, this member stiffness becomes 0. It's ineffective for comparing anything. Now we just have KB over KB. This C is 1. That means the bolt takes everything. If this is 1, this is gone, and all it had, and so that doesn't do anything. Okay. Got that? All right. So with that said, that's our basic relations we're going to learn today. Now we also need to learn about preload. We're going to learn two methods for preload. The first one is the turn of the nut. Once we know what the stiffnesses are of the member and the bolts, we can use a turn of the nut approach to approximate how much force is, did you ever go and you torque something up and you wonder how much clamping action do we actually have? There's two ways to do that. The first way is to turn of the nut, which basically means what happens is, remember when we're clamping that preload, we saw that the bolt force is equal to the member force, which is equal to PI, right? Any deflection, now even though the force is the same, for that force, the bolt will stretch a different amount than the members, usually a lot more. So the total deformation is going to be the bolt stretch plus the member compression. So we can write this relation, which we can write this way, and we get the relation when we note that the deflection is just the number of turns times the lead, remember? Now if we only have a single thread, then the lead is the pitch, so I'm writing that the lead is equal to the pitch here. But remember, that's only true if we have a single thread. So since the amount that the bolt advances is the lead in one turn, the number of turns that we apply times the lead tells us how much deflection, how much that bolt moves, that nut moves. So if we turn one turn, we're going to have that lead is how much deflection we'll have. If we turn a quarter turn, then it's going to be 1/4 of the lead, okay? That gives us this relation, which says that the preload is approximately the number of turns times the pitch. Now remember, this is only if it's a single threaded fastener. If not, we just replace P with the lead, over the stiffness of the joint. That tells us how much preload we get. And remember, both of these start with the same preload. Okay. Now, that's one method. This is the method that I used when I had composite sandwich being squished up with a bolt on the Delta program. Now, if we have, let's say there's another method that's even easier, let's take a look at that. This is called the nut factor approach, and you need to do testing for this. But basically what it does, it says, hey, let's make this simple, and let's come up with this relation. Let's say that torque, T, is related to preload through this relation. So we just need the preload times the diameter of the bolt, that's the nominal diameter, times the K factor. This is not a stress concentration factor. This is a nut factor, okay? Or a torque factor. Both of those terms, nut factor and torque factor, are commonly used. All we need is the nut factor times the preload, or another way to say it is the preload is just the torque that you apply divided by the nut factor and the diameter. Okay? Here are some nut factors or torque factors for different things. Non-plated black finish bolts, zinc plated bolts, lubricated bolts, cadmium plated bolts, and so on. Okay? Now if you look at this table, you'll notice that these numbers don't vary very much. They move from about 10% to about 30%. Okay? Of course, that is a lot of fluctuation, but it's not huge in the big scheme of things. So the nice thing about this is if you don't know how much preload you're going to get for a certain torque, you could say, well, it's probably around 20-ish%. So I can assume a nut factor of around 20%, and it's probably not too far off. Okay? This is pretty simple. The nut factor approach is more useful if you have stiffnesses that are not standard. These values of K are probably for all metallic joints of the same kind being clamped up. If you have a joint that has members that have a different stiffness than we typically see, then those wouldn't be valid. Okay? Now, some common values are recommendations. Shigley recommends to use 75% of the proportional limit or the proof load for non-permanent connections and 90% for permanent connections. Now, it seems like loading the preload to 90% of its proof strength seems like a lot, but what we're going to find is preload has really strong properties for increasing fatigue life of fasteners. The more preload you have, remember when we're doing fatigue, we had two terms. We had the mean stress and the alternating stress, and both affected it. But alternating, the more you change the stress, the more it seems to affect the life. That's especially true for bolts. Because of that, preload has the effect, even though it pushes up the mean stress in the bolt, it reduces the alternating stress, which tends to have a positive effect on fatigue. Okay? So here's some questions. What are two methods that relate torque to preload? Right? Okay? What is an equation to determine preload from turn of the nut? Right? What is P in this equation? Right? And actually, this written correctly would be, the lead would be here. Actually, that would be better for me to write. It's the number of turns times the lead divided by this other term, and the lead happens to be the pitch if we have a single threaded fastener. What's the equation to determine the preload using a nut factor approach? That looks even simpler, right? What's K in this equation? Right? Nut factor, torque factor. What is a typical value of the nut factor? Sure, or 0.2, somewhere in there. Which is better or more accurate to use? So what really the question really is, are you just grabbing nut factors out of a table like Shigley's, which applies to who knows how they tested it, or did you actually develop your own nut factors, or did somebody test something very similar to the thicknesses and stiffnesses and stack up sizes that you're testing? If you have test data from a really similar joint, then nut factor is probably more accurate. If you have test data from some other knucklehead, you've never seen their test setup or what materials they're using, then probably turn of the nut is going to be more accurate. It is more work though. Okay, one more idea is being able to write a margin of safety against joint separation. Remember, it's important that the joints don't separate. If they do, then all of the external load is going to go into the bolt plus the preload, and that's going to have a dramatically detrimental effect on the strength. So here's our approach. If the member force is less than 0, which means it's in compression, then C is valid. If it's greater than or equal to 0, then the members no longer carry any load and the bolt carries it all. We've already talked about this. If we have non-separating joint, we can write our margin of safety against separation like this. Now notice, this is a little tricky. This is the preload divided by the external load on the members. This is not the total load in the members. This is just the external load on the members, okay? And our bolts get evaluated by this equation if we don't separate, and by this equation if we do separate. And we'll calculate our margin of safety in the normal manner. Got it? So that's all I've got for you. This is our first lecture on bolt tension. Next lecture, we'll learn about how to evaluate fatigue for bolts in tension. It's important, critical even, that you understand how to do this. Now, I've done this check a lot less than I've done other checks in my industry experience. Actually, less so in aerospace. When I was working in aerospace, I did this a handful of times. When I got to rockets, I did this a lot, especially when I got to the Delta IV and had all these bolted joints with big, thick parts. So there are going to be, if you work in structures, there will be times when you need to evaluate the tension strength of bolts and fatigue life, and this is your approach. Make sure you understand it. Enjoy.